Okay, so 12-3 and 12-4. Matrices and operations within those. So we're going to do some addition, subtraction, multiplication, things with matrices today. So really, actually, like I said, it's an easier lesson, I think, than what we did yesterday with the systems of equations. It really is. The first thing we want to talk about is the determinant of a matrix. Square matrices only. By square, I mean same number of rows as columns, like 3 by 3, 2 by 2, n by n, whatever, same number of rows as columns. Those are the only ones you can find determinants of. What the determinant is it's like this number that's a property of the matrix. And when you're dealing with matrices and systems of equations, if you took, kind of relate it back to what we did yesterday, if you took the coefficient matrix, so just the numbers that are in front of the letters for a system of equations. So if it's a two variable system, if you took just, maybe it's, 2x minus y equals 7, and then 3x plus 5y equals 9. If you took just the coefficients of the letters, 2, -1, 3, and 5, that creates a square matrix, right? Okay. One of the properties of a matrix equation, like you can convert it, instead of doing an augmented matrix, you can do what's called a coefficient matrix times the variable matrix equals a solution matrix. This is another way of writing a system of equations. This means the same thing as this. It also is the same. When we did yesterday using RREF, we augmented this matrix by putting the 7 and the 9 in a third column and did RREF. That's how we normally solve systems. The determinant of this coefficient matrix here is it decides whether or not that has solutions or not, or if you can solve that system, okay? And that's the property of a determinant. That's what it's useful for as far as matrices go. Now, depending on that number, as long as that number is not 0, then you can solve that system. That doesn't mean we know whether it has infinitely many solutions or just one solution. We just know it has answers if the determinant is not 0. That's the application of it. We're not going to use determinants to solve systems, but it could be used to solve systems. But it also, that property is what that determinant helps us find. Okay, so to find a determinant of a 2 by 2, I'm going to show you how to do this by hand because it's quicker than doing it with a calculator on a 2 by 2. Anything bigger than a 2 by 2, I usually don't do it by hand just because it takes quite a bit longer. Surprisingly, a lot longer depending on the numbers that are in there. Okay, so a 2 by 2 determinant, we're just going to use letters to start off with, A, B, C, and D. Okay. The way that's noted is they use DET, and then they might list the determinant like that. If they want you to find the determinant, they'll say DET and then this. Or they'll use these symbols. Looks like absolute value marks. But if it's around a matrix, it's a determinant, is what that means. So you will see this. You can also see this. Pay attention real close because just glance at it. There's not much difference in an absolute value mark and then these square brackets. Right? They look a lot because they're straight. So make sure you know DET of the matrix is the same as looks like absolute value of a matrix. Not absolute value, but the determinant of a matrix. The way you find that by hand for a 2 by 2 is you multiply the diagonals. You say A times D minus B times C. That will find you the determinant of a 2 by 2 matrix. Okay. So if we were going to look at this system up here, example A, let's say we were find the determinant 2, -1, 3, 5. We'd say 2 times 5 minus -1 times 3. That'd be 10 plus 3, right? Which is 13. What that tells us is for that system of equations, we can find answers. May not be one answer, maybe infinitely many solutions, but it's got answers. That's what that tells us. Tells us that that matrix is what's called invertible, and if the determinant is 0, it's not invertible, but that doesn't really matter to you guys. So, even if there's a 0 and a 2 by 2, you can't. You're always going to do a 2 by 2 this way. You can find the determinant whether zeros in there or not. It really doesn't matter what numbers are in here. You can find that determinant by doing that. Your calculator can also find the determinant. I'll show you how to do that real quick. So go to the matrix menu, and we're going to edit and put a matrix in there. So we're doing 2 by 2 here. Just going to put that same one in there that we used a second ago, the 2, -1, 3, 5. 2, -1, 3, 5. So you get that matrix put in there. Go back to the regular calculator screen, just like we were doing yesterday, and then you're going to the matrix menu. We're going to do some math. So we go over to the math menu, and the very first option is DET. It's determinant. Okay, so you select determinant, and then it says, okay, what determinant of what? So we pick the matrix that we put in. Crank out 13. Through all of that button pushing, I get the same number. Okay, that's why I do 2 by 2s by hand, because it's just quicker for me to just multiply and subtract than it is to type in that matrix, then go through all the rigmarole of finding determinant and getting that matrix in there. It just takes a lot of time. Okay, anything bigger than that is a lot more operations to do by hand. Okay, so a 3 by 3 turns into actually having to find 3 2 by 2 determinants and then multiply by numbers and add and subtract. So there's 1, 2, 6, 9, 11 operations to find the 3 by 3s, as opposed to 3 operations to find the 2 by 2. A 4 by 4 gets even larger, because a 4 by 4 you break it down into 4 3 by 3 determinants. So that's 44 operations. And then, and for the 3 by 3s, and then you have to still multiply 4 times. So that's 48 operations. And then you've got to add and subtract 3 times. So that's 51 operations for a 4 by 4. It goes up really fast. Anything bigger than a 2 by 2. Mm-hmm. Yeah. If you're planning on being an engineer, you'll take a linear algebra class. It may not be called linear algebra, depending on your vein of engineering you're going into. They've got different names for them, but it's basically all of them are linear algebra, and you do tons of matrix stuff there. And by my calculator, you're doing it all hand stuff. So yeah, we did those by hand. It's not that bad. Once you get used to it and you've done it a lot, it's just arithmetic. You just don't make mistakes. It's tedious. And so there's a lot of places to make mistakes. So if you got anything bigger than a 2 by 2, calculator's the way to go. Okay, so let's look at one that's bigger than that. So let's find the determinant of this 3 by 3. 2, -1, 3, -2, 5, 1, 0, 6, -9. So got a 3 by 3. It's a square matrix. If it's not square, then you can't find the determinant anyway. You'd say undefined. And so that's what you, if it's not a square matrix. Okay, so we're just going to find the determinant of that using the calculator. Second matrix, edit. Let's go to a 3 by 3. 2, -1, 3, -2, 5, 1, 0, 6, -9. And so second quit. And then since I put it in in A, I could just do like I did yesterday and go up and grab that command and then crank out the -120. If you forget that you can do that, you just hit second matrix, math, operation 1, matrix A, -120 is what we're getting there. Are you sure? Make sure I typed in the right numbers. Yeah. 2, -1, 3, -2, 5, 1, 0, 6, -9. Check, make sure you got them right. It will not give you a different number if you typed them in correctly. Anybody else? Did you find your mistake?
Is it -5 or
-9.
so it's not -5 on page 100? Yeah, I wrote -5.
So pretty much you use the word numbers.
Not necessarily. I mean, how do you know it's a weird number? You don't. There are really no weird numbers.
Yeah, I got -1.
Okay.
I thought it was -5.
All right. So determinant, really easy to do. Now, I've got to mention this thing that exists. There's a thing called Cramer's rule. And what it's used for is solving systems of equations using determinants. It exists. That's all you need to know. Okay. Somebody says, hey, you can solve this using Cramer's rule. Know that, they're talking about solving a system of equations using determinants. So you've heard of Cramer's rule before. We're not going to use Cramer's rule. How do we solve systems of equations? What did we do yesterday? REF. That's the way we're going to solve systems. Okay. It gets the exact same answers. What you end up doing with Cramer's rule is you find the determinant of, depending on how many variables you have. If you've got a 2-variable system, like a 2 by 3 augmented matrix, then you have to find the determinant of 3 separate matrices and then use those to find your solutions. If it's a 3-variable system, you've got 4 different matrices to find the determinant of and use those and do some division and stuff with that. It works. It's wonderful, but we have reduced row echelon form, which really works great and is quicker. So that's what we're going to use. So you've heard of Cramer's rule. I've checked the box that we've talked about Cramer's rule. All right. Now let's do some matrix operations. Some of these I do by hand. Some of them I do with the calculator. They can all be done in the calculator, but not necessarily advantageous to do any of them in the calculator if you can multiply without a calculator. Okay, the first operation we're going to talk about is scalar multiplication. The lines are so blurred I can't even tell you anymore. With that, so scalar multiplication, I would guess probably it is 12-4. Either that or 12-3. I'm not sure. So Scalar multiplication is like distributive property. That's kind of what you want to think. So when you're doing scalar multiplication, they might tell you to multiply an entire matrix by -2. It doesn't matter what size the matrix is. Here I've got a 3 by 3. You can multiply with a scalar multiplication any size matrix. It doesn't matter. Okay? There's no rules about sizes with scalar multiplication. It's just multiply everybody in that matrix by the number that's outside. All it is. So we're just going to double and change the sign of everybody. So that'd be -6, -12, -8, -16, +12, -14, 10, -6, 0. And you've done scalar multiplication. You can do that in the calculator. You'd put this whole matrix in there, and then you would tell your calculator -2 times matrix A, and it crank that out. I don't know that that's, I don't know that I've ever done scalar multiplication in the calculator, just because it's too easy to just do the math. Okay, so you can do that with the calculator if you want to. Don't have to. All right. Now, we talked about scalar multiplication. Let's talk about addition and subtracting. If you're going to add and subtract matrices, they must be equal sized. Okay, so if you've got a 2 by 3, to add two matrices together, they both got to be 2 by 3s. They both got to be 4 by 4s or 4 by 8s. Whatever the size of one of them is, the other one has to be the exact same size in order to add it together. Okay, so matrix addition or subtraction, they got to be the same size. If they're not the same size, it's undefined. Okay, if they're not the same size, it's called undefined. All right, so let's look at an example. 2, -6, -5, 8, 10, -11. What size is that matrix? It is a 2 by, or say 3 by 2. So if I'm going to add something to that, it has to be what size? It's got to be 3 by 2. So let's make one up that's 3 by 2. -5, -8, 13, 6, -14, and 4. The way matrix addition or subtraction, they both work the same way, is it's corresponding elements. Elements are the numbers that are inside. So the 2 is in the top left, first row, first column. It has to add to the first row, first column of that one. That's why they have to be the same size. So 2 plus -5 gives you -3. And then -6 plus -8, -14. And then -5 plus 13. 8. 8 plus 6. 14. 10 plus -14 is -4. -11 plus 4, -7. And that's your sum of those two matrices.
So if they're different sizes, you could put them like this.
It would give you an error. It'd give you a dimension mismatch error, which is just
I didn't know if the matrix was just a number that you could.
When you could put these two matrices like this, you could put this one in as matrix A, the left one is matrix A, this one is matrix B, and then then tell your calculator matrix A plus matrix B, and it would crank out this matrix. A lot of button pushing to get it to do just addition, but you can do that. If they don't match and you just forget that they've got to be the same size, and you try to add maybe a 3 by 2 and a 2 by 3 together, it's going to give you an error, and your calculator will say dimension mismatch. I think I actually can show that error here, maybe. Yeah, I got a 3 by 3 and a 3 by 4. They're not the same size. So if I take matrix A plus and then go get matrix B, I'll show you what the error you get is. It says error dimension mismatch. They're not the same size. You can't add things that are not the same size. That's what it's telling you. And so check size dimension, the list on the matrices, and then so it's telling you everything you need to know out of that. But so if that's the case, if they're not the same size, the answer is undefined. Because you cannot, it's not a defined operation to add two different size or subtract two different size matrices. Okay, easy thing. Now, they could mix together scalar multiplication and addition or subtraction. Which one should happen first? Why? Yeah, because the order of operations. The scalar multiplication is going to happen before the addition or subtraction. Okay? So just make sure you follow order of operations. That still applies with matrices. Matrix addition is still commutative, just like regular numbers. 3 plus 4 is 7. 4 plus 3 is still 7. Addition is still commutative, just like it is there. Subtraction never was commutative, so it's still not with matrices. So you can't swap the order and get the same answer with subtraction. Okay, addition you can. That relates to the next thing, which is multiplying. Multiplying matrices, they don't have to be the same size. In fact, sometimes if they are the same size, you can't multiply them together. The rule for multiplying matrices is when you look at the multiplication that's happening, you've got row by column, right? That's how you name the size of a matrix, is row by column. So it's 2 rows, 3 columns, something like that. And then the other one next to it that you're multiplying times, it has a row number and a column number. So maybe it's a 3 by 4 or something like that. The columns from the left one have to match the rows from the right one. Okay. So when you're multiplying, example would be something like, if I'm going to do a 2 by 3 times a 3 by 4, that's legal and doable because those two in there match. When you do that math and do that multiplication, the answer will be a size 2 by 4. The outside numbers tell you what size the answer is going to be. Okay. If you had something like a 3 by 6 times another 3 by 6, these numbers in the middle, they don't match. So that means it's not possible to multiply those together. So you would write undefined. Okay, the columns from the left matrix have to match the rows from the right matrix for you to be able to multiply them. Okay. I normally don't ask my students to multiply matrices by hand, because it's one of those things where it's a lot of operations in order to get the result. It's doable and easy, but you got to multiply depending on the size of the matrix that you're dealing with. So if we had something like this, for an example, we had matrix 2, -3, 5, -7, -8, 12 times 10, 11. What size is this matrix? 3 rows by 2 columns. What size is this matrix? 2 by 1. Can I multiply them together? Yes. These things right here, the columns from the left one match the rows from the right one. Okay. That means when we do that multiplication, what size should our answer be? 3 by 1. Okay. It's good to know that, because if you use calculator to do this and it doesn't give you a 3 by 1 back, that means you did something wrong. You put something in wrong. Okay. Good to know that. Now, I'll show you how to do it by hand, but we're going to do it with the calculator most of the time. Okay. The way it works is you take this row times this column and you add the results. So you take 2 times 10 is 20 plus negative 3 times 11. So 20 plus negative 33 would be negative 13. And then this one's easier because the second matrix is pretty small. So then you take this row times those numbers in that column. So 5 times 10 is 50. Negative 7 times 11 is negative 77. So that would add together to be negative 27. And then you take this row times that column. Negative 8 times 10 is negative 80. 12 times 11 is how much? 132. And 132 minus 80. 52. And you can do it that way. That's how it works. When you get a larger one here and your resulting matrix is not one column, there's a lot more operations that have to happen. Okay, so it's not the easiest of things to do by hand. Doing it with the calculator is a lot easier. So let's do that with the calculator just to make sure we're correct. Okay. So we go matrix, edit, and I'm going to put in a 3 by 2, 2, negative 3, 5, negative 7, negative 8, and 12. And then go in and put matrix B, say 2 by 1. And 11. So you put the matrices in there, and then you're just going to say matrix A times matrix B. And there we crank out that matrix out of that. Okay. If you forget the rules about the size and you went ahead and put those in there and tried to multiply them together and they don't work, it's going to give you the same error we got earlier, that dimension mismatch error, and you'll know that it's undefined. Or at least you'll know to go back and check and make sure you put your matrices in the right way. Okay. So multiplying matrices, definitely one of those things I would do with the calculator, not do it by hand. It's not, I'm not going to ask you to do it by hand and show me your work or anything like that. Okay. I'm just going to give you a couple of matrices and say, multiply those suckers together. That's all I'm going to ask. Okay. All right. Let's look at the inverse of a matrix. To find the inverse, you got to have a square matrix with a determinant that does not equal 0. Okay. What we're finding when we find the inverse of a matrix, we're finding that what's considered the multiplicative inverse of a matrix, which if you think about regular numbers, we think about the regular number 3. What is the multiplicative inverse of 3? I don't know what that means. It's got another name that we use normally. We don't say multiplicative inverse. We use an R word. It is a rational number, but
Reverse.
no, reverse. Reverse is a gear. mathematical operation. Some of you are almost saying that you're scared to say it loud enough right here. Yeah. Reciprocal and multiplicative inverse are the same thing. Reciprocals, multiplicative inverses are the same thing. The reason they're multiplicative inverses are that if I say 3 times its multiplicative inverse, what's the result? 1. Okay? So with a matrix, if we're finding the inverse of it, and we multiply matrix A times its multiplicative inverse, then I'll get what's called an identity matrix back, which is the 1. Matrix world, it's the 1. When we're solving systems, we got that 1, 0, 0, and then a number over here, and 0, 1, 0, some other number, 0, 0, 1. All of this over here is a identity matrix, meaning it's 1x, 1y, 1z, that idea. It's 1 of each thing. That's an identity. In mathematics, in regular numbers, 1 is the multiplicative identity. An identity property says, whatever I multiply times the identity, I get the same thing back. So if I multiply a matrix times the identity matrix that's the same size, I'll get that same matrix back. It's like multiplying by 1, is what that is. All of that's big fancy talk for stuff you don't really have to know, but I like talking about it because this is one of my favorite topics, but it's fun to me. That it all makes sense. That the world turns on the right angle and axis and spins perfectly so that all the math makes sense. And it's wonderful. So if we're going to find the inverse, it's got to be a square matrix and the determinant cannot be 0. If the determinant of a square matrix is 0, then it's not invertible. Okay, so if you try to find the inverse of 1 and your calculator gives you an error, then that means, oh, the determinant of that thing must have been 0. Okay, as long as the determinant is any other number, it doesn't matter if it's negative 167 or positive 2. As long as it's not 0, you can find the inverse of it. But it's got to be a square matrix to find the inverse. Okay. Now, the way that an inverse is really found, if you did it by hand, and yes, you used to have to do this too, and high school students used to have to do this too. We don't make you do it anymore because y'all are spoiled because you got a graphic calculator. They used to not exist. Is row operation. You know all those row operations like it's on that quiz and stuff? You have to do a certain set of row operations in order to move that matrix around so that it would. Let's just look at an example. I'll show you what I'm talking about. So let's say matrix A is this 2 by 2, 3, 3, negative 5, 6, 4. Doesn't really matter what the numbers is, as long as I make it not have a 0 determinant. Okay, so we got a 2 by 2 there. What happens is to find the inverse by hand is you set up this thing and then you put an identity over here that's the same size, and then you start doing all these row operations so that you turn this into a 1, that into a 0, this into a 0, and that into a 1. And what ends up showing up over here once you do the correct row operations for doing that is the inverse matrix. It takes several steps, even for a small one like this. There are several row operations that it would take to get that to happen. We don't require you to do that, but that's what your calculator is doing in the background, just so you appreciate the nicety of pressing one button and getting an answer. Okay, to find the inverse of that matrix, inverse notation. You know, we did function inverse back in earlier in the book, chapter 5, I think. A inverse is a to the negative 1 power. That's the idea. So we're going to put that matrix into a calculator. Second matrix, edit. Got a 2 by 2 this time. And we got, what, 3, negative 5, 6, 4. 3, negative 5, 6, 4. So you just put that matrix in there. Go back to your regular calculator screen. Tell it to use matrix A. And then the inverse button on your calculator is right here. It's the same button you've been hitting to go to the matrix menu. You just don't hit second first. If this x to the -1 power is the inverse button. You hit inverse. And gives a bunch of decimals. I'm going to convert that to fractions. So hit math, enter. Not too pretty, but it's still there. So we got 2 over 21, 5 over 42, -1 over 7, and 1 over 14 out of that. That's your inverse. 2 over 21, 5 over 42, -1 over 7, and 1 over 14. That's the inverse. To verify inverses, so if you do a 3 by 3 the exact same way. So you type in a 3 by 3, tell it to do the inverse. It does it the same way. Okay, that's all I'm asking you to do. Now, if they want you to verify inverse matrices, absolutely. A times A inverse should give us an I matrix. So if it's a 2 by 2 matrix, so if we're saying matrix A was the one we used, 3, -5, 6, 4, and they said matrix B is this weird one we found, two over 21, -1 over 7, 1 over 14, 5 over 42. That's the right number. Yeah. And they want us to verify that if they're inverses of one another or not. Example G. Then we just multiply A times B and see what we get. So in my calculator, I just need to go in and use this matrix, this inverse here, or that, B. I would go to my matrix menu. We'll go edit, and I didn't mean to edit that one. Let's go matrix again. Edit. I want to edit matrix B.
Go back up there and grab that.
You could, but the idea is that when you're doing the problems, you won't have that out of that. Or you could find the inverse of matrix A and see if it matched matrix B. If it does, then you got then they're inverses of one another. But you got 2 over 21, 5 over 42, -1 over 7, and then 1 over 14. So if I say matrix A 1 times matrix B, they call it I2 because it's 2 by 2. All identity matrices are squares, so it's I2. So it's 1, 0, 0, 1. It does match. So A and B are inverses. That's what we found by doing that. Okay. If you multiply two square matrices together and you get an identity matrix back, then they're inverses of one another. This is when they're inverses of one another, this is the only time that matrix multiplication is commutative. If I said B times A, I'd still get the identity back. Any other time, matrix multiplication is not commutative. Okay? The only time it's commutative is if they're inverses of one another. So be careful. If it says A times B on your matrix that you're supposed to multiply together, make sure you put it in that order because it matters a lot with matrix multiplication. All right. There's no such things as matrix division. Doesn't happen. matrix division does not happen. All right. There's some practice problems there. Let's see, we got about 30 minutes left in class today. We'll do work day tomorrow, and that'll allow those folks to catch up on their quizzes from the day, and then we'll quiz Friday, and then get the next lesson Friday, and then probably be work day on Monday next week. I'll have it ready tomorrow. Sure, yeah, I know, yeah, of course, folks, y'all got something out from me. But, yeah, if you wanna take the quiz tomorrow, if you don't wanna take it during class tomorrow, we'll be here till 10 anyway. So that should be, you're probably okay to take it tomorrow during class, but if not, you can come back during either 4th or 5th o'clock. And take it. Yeah. So.